I've been teaching geology for nearly 20 years, and the most contentious discussions that I've ever heard have been about climate change. I've taught geology, I've taught natural disasters, I've taught environmental science, I've taught introductory classes, I've taught junior, senior level classes, and the single topic that causes the most rancorous debate is climate change. So what I wanted to do is I wanted to break down the concept of climate change, ice ages, carbon dioxide, all of the things that are wrapped up in this debate. I wanted to actually discuss those, and I don't want to just give my 2 cents on the issue because the world doesn't need 2 cents. But one of the things that you'll often hear in the debate, you'll hear climate scientists, you'll hear people being interviewed, they'll have their credentials next to them, and I could do those things, right? I have my master's degree in geology, etc. But many times when you hear something about this debate, you'll hear it said in this way. We have to listen to, for example, just the climate scientists, or we need to listen to just these people. And I understand why that is, right? We have these people that their expertise is in a particular topic, and we want to hear what they have to say. But because of how politicized the debate has gotten over climate change, whether it should or not, and we can discuss that, one of the things that often gets lost is this. If climate change is occurring, and if it is so obvious for us to discuss, then a person with a science degree who has been trained in the process of science should be able to look at the information for themselves, break it down for the common man to actually see. The common man should be easily able to see it. And I hate using that expression, common man, because what does that mean? But it's one of those things that it's sort of like, I wanted to go out and I wanted to understand it for myself. And I figured that if I understood it for myself, if I could put it in my own language, if I could put it in my own words, then other people would be able to understand it as well. So let's talk about climate change, global warming, ice ages, all of those things. The way that we're going to have to do this, though, is the topic is huge. So I wanted to break it down into 5 sections. First of all, the basic science. What affects climate? What's the difference between climate and weather? Short-lived climatic cooling, and that we're going to talk about volcanoes. You've probably heard the statement many times, well, the volcanoes are doing more things. Okay, we're going to talk about those. Modern changes, politics and misinformation, we have to talk about it, and then what can be done, and the questions that surround it. Because I've given a lecture that is similar to this to different groups. I've given it to the Rotary Club, I've given it to young people, old people, it does not matter. I've given this lecture many times. And what I want to do is I want to focus on the basic science of it. In order to do this, we have to talk about how science is done or how it should be done. And while this might seem presumptuous, there's a reason for this because we use specific vocabulary in science that many times we don't use in the public space. And the most misunderstood word is the word theory, because we tend to use the word theory like we use the word idea, like I have a theory. Why did he get into a wreck? I have a theory. Well, no, at best we have a hypothesis, we don't have a theory. So let's break down these 2 words, hypothesis and theory. Hypothesis is an educated guess that's supported by observations. You see a giant cloud of energy in it, like in a ball form, what we would call ball lightning or something, and it passes across the landscape, and you go, I've never seen that before. But you're situationally aware, you saw that you had a storm, there was some weird things happening with the power lines. You look up and you see all of these things, and you go, okay, I have an idea that may explain what caused that. It is an educated guess, supported by the observations. We're trying to explain some aspect of the world. A hypothesis must be testable. If we develop an idea, that idea has to undergo, survive scrutiny. It has to survive various experiments done to either recreate it or explain it or disprove it, something. One of my favorite examples of this, and yes, they do use the word theory incorrectly, but they use it because it just doesn't sound right. One of my favorite examples of this is actually Buffy the Vampire Slayer, the 90s television show. They had an episode called Once More with Feeling, which was ostensibly about a dancing demon. Everybody wakes up and they all start singing and they all start dancing. And one of the crew, Buffy's crew, Xander, he goes, I have a theory, a dancing demon. He had an educated guess based upon his observations. And now, he used the word theory, not hypothesis, but it wouldn't really work with that song. And people look at him, they go, that's nonsense, etc. So he throws open the window, he looks down, and there is a laundromat, and the guy comes out of the laundromat, and he's holding up his suit, and he's got a whole bunch of people around it, which all strike a pose. And he goes, they got the mustard out. And they go, yeah, okay, that's probably because it's a test, right? He came up with an educated guess, supported by his observations. He tested it. So you'll never hear me sing again here because I don't want to ruin you. So how does that differ from the word theory? Well, theory is a much more large-scale concept. It is a collection of all tested hypotheses that relate to one large-scale idea. When we talk about something like the theory of plate tectonics, we are bringing together a whole bunch of individual research on how a volcano works and then how volcanoes might work. We study lots of individual volcanoes. We study lots of individual faults trying to understand how earthquakes work. We study a lot of individual physiographic landforms, mountains, valleys, cracks, hills, folds in the earth. And after we come up with explanations for all of those little things, we take a step back and go, something has deformed Southern California, for example, or Oregon and Washington, for example, to build valleys and mountains, to build volcanoes, to cause earthquakes, to have big cracks in the ocean. And we go, and we try and tie all of that together to come up with one big picture that the Earth's surface is broken up into a bunch of individual pieces, and those pieces bump and they grind and they slide apart. And as they interact, they generate earthquakes and volcanoes and mountains and valleys. We've come up with one picture that has many facets, and each one of those facets had to undergo a rigid scrutiny, right? Sure. And we have this grand overarching explanation for, in general, how one aspect of the earth works. Is it a fact? No. A fact is, this is a hand, right? That you can look at a hand. A fact is you were looking at a screen, you were hearing my voice. Those are facts. But because other observers can hear my voice and then go, he is speaking. We don't know what he's speaking on. We don't know what medium he's transferring to us. We know that it's being delivered to us over the computer, right? We have individual little facts. We are looking at what we all agree is a screen. We have a light that is shining on my incredibly bald head, etc. But when we have this giant overarching idea, it's the best explanation we have for a big level thing that we have been able to figure out to date. And that's what a theory is. So how science should be done. We observe, we make an educated guess, we test that educated guess. If that educated guess seems to be valid in the confines of our test, we try and repeat that elsewhere. What do we get? We eventually get a whole bunch of pieces all figuring together, and then somebody goes, the theory. Evolution is the same way. We have things with genes, gene theory. There are a whole nebular theory, right? How the solar systems are formed, etc. So how science is done, hypothesis versus theory. So let's talk about climate. First, let's talk about the difference between the word weather and the word climate. Weather is short-term, day-to-day phenomena. Climate is long-term, year-to-year or decade-to-decade phenomena. So the difference would be, today it might be rainy, tomorrow it might be sunny. But in general, the deserts are dry and hot during the day and cold at night. The rainforests are generally hot and rainy during the day. So that is what we would expect long-term, climate. Weather is changes. Today we might get 3 inches of rain, tomorrow no rain, the next day 4 inches of rain. So that's the difference, short-term versus long-term. So let's look at an average day or a general idea about how heat moves through the earth, because one of the things about climate change is we're talking about, is the planet heating up, is it cooling down? Well, we need to understand how heat moves through the system. So my incredibly extensive diagram here made in PowerPoint, we have two things going on here. We have yellow, which represents visible light coming from the sun, and red, which represents heat given off by the earth. Now, we could spend an incredible amount of time talking about wavelengths and all of that stuff, but we are talking about visible light and infrared heat, okay? If you look at that, we see some things here, reflected, released, absorbed. we receive 1/2 billionth, so 1 with 2 billion under the fraction, of the sun's total energy. If we were any closer, we'd probably burn up and be like Venus. If we were any farther away, we'd probably be frozen. So we are in the just right zone, what some scientists have called the Goldilocks zone. In our distance from the sun, we receive 1/2 billionth of the sun's total output. And that can change depending on the seasons. Sometimes we get a little bit more on one side versus the other, depending on what's tilted toward. But on average, we get 1/2 billionth of the sun's total output. But when that energy comes to us from the sun, in this case, the yellow rays, the atmosphere, the clouds, and the surfaces of the earth, whether they be water or trees or ice, reflect some of that sun to space like a mirror. So the visible light comes to the earth, 25% of that visible light is reflected back to space by the atmosphere and the clouds, here represented by the blue cloud shape. 5% of it is reflected from the surface of the earth. Now, some surfaces reflect more. White things, light-colored things reflect more energy than dark-colored things. This is why a concrete parking lot is better to stand on than an asphalt parking lot. But on average, 5%. Now, when you hear that, you might think that statement that you might have been taught when you were a kid, which is, well, that's why the sky's blue. It reflects off the oceans, and that's what he's talking about. Well, we could spend an incredible, and I'll record a lecture on that, why the sky is blue. But it isn't because it reflects off the oceans. If it was, okay, maybe over the oceans the sky's blue, but what would it be over the deserts? Tan? What would it be over the forests? Green? So it isn't reflection. There's something else going on there. It is reflecting light, but that's not why we have the color in our sky. We're going to talk about that in a separate lecture. So let's say that that's correct. We get then, if we add those up, 30%. So we only get 1/2 billionth of the sun's total energy, and 30% of that is just reflected back to space. So what happens to the rest of it? It's absorbed by the atmosphere, the clouds, and the land. Now, why do I make a distinction between atmosphere and clouds? There are invisible gases in our atmosphere that are essential for our life. There is the ozone layer in the stratosphere that protects us from most ultraviolet radiation. There is oxygen in the atmosphere for us to breathe. There's nitrogen in the atmosphere, which get affected by bacteria to help us grow crops. That's all the invisible atmosphere. We rarely see it. The clouds we see as condensed water vapor, and that's what represented here, all that represented together. So we can look at water, carbon dioxide, methane, smog, aerosols, particles, all of that I'm just lumping together as the atmosphere and clouds. Well, who cares? Well, when an object absorbs energy, it is always then giving off energy. But the energy that it absorbs and what it gives off are different. When you go outside and you get sunlight hitting you on the shoulder, you are absorbing visible light energy. And what do we notice? Our skin warms up. If you take a rock and it's cold and you set it outside in the burning sun, it warms up. But it doesn't glow like the sun does. So the energy that it gives off is much less than what the sun gives off. And specifically, we could spend time talking about wavelengths. Sun gives off short wavelength, we give off long wavelength. And what's the difference there? Visible light, we're just going to lump together a short wavelength. Long wavelength, we're going to show here by the infrared. And we'll watch the video that I will eventually do on why the sky is blue, because then we can actually talk about that. But light comes in, heat is given off. That's what the red is. So when something warms up, it's still just giving off heat. Sun warms it, gives off heat. Okay, so if you look there, what do we see? 30% of the sunlight is reflected. The other 70% of it is absorbed by the clouds in the atmosphere or the surface of the earth. That's 70 total percent that's absorbed, and therefore is useful in heating up the earth and driving all of the systems, driving moisture through the system. But look at the red arrows. It says 50% is released from the surface of the earth and 20% from the clouds. So whatever we take in, we must give back. It doesn't happen immediately, and this is how we stay warm. Why do I say that? If you look at the planet Mercury, it is baked by the sun on the side that faces the sun, and the other side freezes. One side can reach over 400 degrees, the other side is minus 170 degrees. Why? Because there's no atmosphere to help trap and temporarily store that heat. So it's just bang, being heated by the sun, sunlight shuts off, there's nothing to trap it. Very quickly, the rocks go back to being their regular temperatures, which is the temperature of space, basically. Right? So how does this work on Earth? Well, the easiest way, think about a Hot Pocket, right? When you take a Hot Pocket, if you've ever seen those, it's a meat-filled Pop-Tart that has a sleeve that goes over it. And the sleeve looks paper, but when you take the sleeve off, on the inside it looks like some sort of aluminum foil. It isn't, but it's some sort of like foil-ish item. Well, what happens is when you put that in the microwave, microwaves go in, move through the paper, hit the food warms, heat is given off by the food. As that heat is given off, it hits that foil, which is pointing downward, and the heat is driven back into the food, and so it can much more quickly cook the food than just sticking in the microwave without the sleeve, right? It's only 2 minutes, and you'll have cancer. So when we have this is the way our atmosphere works. Visible light comes in, bang. Some of it's reflected off the space, the rest is absorbed, and what is absorbed is then radiated off from, in this case, 50%. Most of it is radiated off from rocks, trees, twigs, the ocean, and when it comes off as heat, the atmosphere acts like that metal foil and will reflect some of that heat back toward the surface. How do we know this? Well, on a cloudy day, then more light hits the clouds and is reflected off to space. It feels cold. On a cloudy night, we actually feel warmer than on a cloudless night. Why? Because the clouds sit here and can reflect some of that heat more effectively back to the Earth's surface, like the Hot Pocket. On a cloudless night, the atmosphere doesn't really do that good of a job. It's still doing a job, and some more of that heat is able to escape, so it feels colder. So what is the point of all this? Sunlight warms the planet. The planet gives off heat. That heat bangs around in the system for a while and is eventually released to space. Why do we want it to be exactly this? We absorb 70%, we give off 70%. We don't want a net increase in heat. The more heat, if we stored any heat long-term from the sun, then that would continue accumulating and accumulating, accumulating, we'd burn up. So we do give off the heat back to space. By the next day, we get a new supply. So we never run to nothing. That's what we get. We get a low, then we come back. Does that make sense? So how does the Earth store heat? So why do we care then about, say, for example, you hear carbon dioxide, it traps more heat. That means we're still going to give all that heat back to space, but it stays in the system longer, so it heats us up longer, right? The cold nights with the cloud, or the warm nights with the clouds would be warmer. Okay? Does that make sense? So everything, that's the question that we have to discuss is, are we just making everything warmer? So now on to a busy diagram. Why would I do this to anybody? If you study climate change at all, one of the things that you'll know about climate change is this. It is busy. Climate change is a remarkably busy, diagram-heavy discussion. You'll see people throw up charts and graphs and everything. Blah, blah, blah. It's just an assault of information. So when we have that assault of information, we need to be able to look at it, understand what we are seeing, break it down. When you see a graph like this, there was a study that came out that said that teachers have graphs, charts on the screen for maybe 15 seconds because our brain's always thinking, let's go to the next one, let's go to the next one. We're not going to do that. We're going to dive into here. So first of all, title, daily cycle of radiation and temperature. So we're going to look at temperature of the Earth, and we're going to look at energy coming from the sun. We have 3 different lines here. We have incoming, outgoing, and temperature, right? Black, blue, red. The incoming and outgoing radiation we see on the left side of the image, temperature on the right side, but it really doesn't matter because we still have the lines. They are scaled. There are no numbers on there, but they are scaled. And we're going to talk about why that's important. Bottom axis is time of day. So when you see 6, that's 6 a.m. When you see 18, that's 6 p.m. because it's 12 plus 6, right? This came out of Michael Baker in the COMET program. So let's look at the big yellow swath in the center. Let's look at the incoming radiation, the black line. right at sunrise, when we rotate on our axis and a portion of the earth that was not able to see the sun is now able to see the sun, we get an increase in solar radiation. Why? Sun was shining on one portion of the earth. Now that rotates out of the way, it now shines on a new portion of the earth. If we look at any particular point on the earth, it follows a pattern like this. We start getting an increase in radiation at sunrise, we reach our maximum sun angle, and therefore our maximum incoming radiation at noon, and then at sunset, it disappears. Why? Because we've rotated in such a way that we are now hidden from view of the local people from the sun. It's on essentially the other side of the planet. So if we look at it, it does not matter if you live on the equator and at some points of the year the sun is directly overhead, or if you live near the North Pole where the sun is always low on the horizon. This is what you would see throughout the day. The only thing that would change would be the magnitude of this, how much total energy you get versus how little you get. Let's look at outgoing radiation. We see that outgoing radiation reaches its limit, its lowest limit, right around sunrise, and then it increases and then it decreases again. Why? Well, we're going to talk about that, but I want you to notice one thing. If you look at the outgoing radiation, it doesn't exactly follow the incoming radiation. And the reason why is because it's not just we get sun, we get energy, we lose energy, bang. Otherwise, they would follow the exact same trajectory. What it means is that some of that energy stays in the system, and it stays in longer than you would expect it. Why? Because we have an atmosphere that bangs that red, the infrared heat around in the system for a while. So it is, as the sun increases in incoming radiation, we get an increase in outgoing radiation, but there is a lag between when we reach maximum incoming and when we reach maximum outgoing, because it takes some time for that energy to start leaving the system. Look at temperature. Temperature reaches its lowest right around sunrise or shortly thereafter, and it reaches its maximum temperature about 3 or 4 in the afternoon. Why? Well, if we were just dealing with rock heats up quickly and cools down quickly. But because it takes some time to heat up and some time to cool down, even if we got maximum sun angle, that wouldn't be maximum temperature because it still takes some small amount of time to heat up the rocks. So the maximum temperature would be shifted a little bit. For it to be shifted about 3 or 4 hours, that's because water takes a much longer amount of energy to heat up, which is why we make that statement, the watch pot never boils. Well, of course it does. But it takes some time for it to do that. So one of the things that we find is that temperature lags behind both the incoming and the outgoing solar radiation. Does that make sense? Because the visual that we have is this. Sunrise happens, it's cold, we reach our minimum temperature right around there, solar energy is increasing, we start increasing the amount of outgoing radiation. It takes some time for us to actually heat up the planet. And then as we heat up the planet, then as that energy starts going out, then we start cooling. So what's going on here? We have several things to think about. Sunlight coming in, that's all represented there in that yellow swath, energy going out, and the temperature of the planet. And the temperature tracks more closely with the outgoing radiation than it does with the incoming, because that represents the heat energy that everything is giving off to space. Right? Notice one thing that never happens. We never hit a zero. We never hit a zero as in we've gotten rid of all the outgoing radiation and then we just get a new batch. We never get to zero temperature, whatever that is, right? Absolute zero. We don't do that. Even though there are no numbers on here, you notice we don't hit a zero. And that's because every day we are getting more energy and we are giving off some of the previous day's energy so that some energy is always moving through the system. That is a busy diagram, but if you take time to actually look at it, you go, oh, I see what's going on here. Let's think about it another way. I was giving a lecture on bank accounts. Specifically, I was giving a lecture on climate change in business, and I thought, you know what? Here might be a good analogy. In the concept of one day, if the planet cools down, we can think about it as having a thermal loss. We are losing heat. We are reaching the lowest point for a day, and we can think about that like an expenditure. Why? In the morning, when a business opens up, all of the first portion of the profits for the business go into paying the opening costs, paying the workers, but toward the end of the day, we start getting a net profit, right? Our profit to loss increases toward the end of the day. We require a lot of solar income to exceed the thermal expenditures. So maximum profitability occurs later in the day. If we look at a year, think about this. It's cold in wintertime. In spring, we start warming up. It reaches the peak of temperature when? About August. Why? The longest day of the year is June 21st in the Northern Hemisphere, right? The longest day is June 21st, but it takes us until the middle of August to reach our peak temperature because we have to heat up the water. So long term, that's when we start hitting our peak profitability. And then we lose heat and we start cooling through fall toward winter. In business, sure, we could talk about it, but we still get the same idea. We get our peak profits around Black Friday or later, depending on the nature of markets, right? So the peak profitability increases toward there and then drops after Christmas. Everybody spent their money. There's no money after Christmas. In business, you want a net profit. You want throughout the year to have gained from all of the losses that you have to spend, all of the people that you have to pay, the business, the property tax, etc. You want to gain a net profit. You want money each year to have more and more than you had the last. We do not want that on Earth. If we use that same analogy, and this is where that analogy breaks, the net gain in energy would result in higher temperatures and the Earth would burn up eventually. Does that make sense? I figured that might be another analogy that we could use. So now that we understand, that's how the difference between weather and climate, and that's how climate works. That's how the general heat budget of the Earth works. Right? Let's talk about ice ages. An ice age is very simply this. It is we have ice on Earth in the Arctic. We have ice on Earth in the Antarctic. We have ice on Earth in tall mountains. We call those, if we just have snow that just lays there, we have snow fields. If we have enough snow that it compresses under its own weight and starts moving under the influence of gravity, not an avalanche, but it moves as a coordinated mass downhill, we call that a glacier, and specifically we call that an alpine glacier after the Alps. In a glacier, if you've ever been to a glacier, like is shown here in the upper right-hand picture, if you've ever been to a glacier, glaciers, if you were to put an object on the surface of that glacier over days, weeks, and months, you would actually see that object move because the ice which is there is always moving downhill. Even if a glacier is melting and it looks like the glacier is melting backwards toward the summit of the mountain, the ice is still moving under the influence of gravity, can't do anything else. So that is always a system that we have alpine glaciers and the material moving downward, but there ends where we would say the toe of the glacier, the end of the glacier, that end, if that ever starts to move in the Northern Hemisphere, down into the northern latitudes, down the side of the mountains, out into areas where we wouldn't normally expect it, that's what we mean when we talk about an ice age. A time when alpine glaciers expand into the northern latitudes. And the ice sheets, we have vast deposits of ice, for example, in Greenland. You've heard the Greenland ice cap. The Greenland ice cap is a massive blob of ice that the base of it is being squeezed under the force of gravity, the pressure of everything above, and it is spreading, but the edges of it are melting back. So even though it's spreading from the center outward, the edges are melting back, and so we generally don't see it leave Greenland. If it does and starts spreading to cover the northern latitudes, then we would call that an ice age. And what does that mean? In the last ice age, we actually had ice cover an area in North America, for example. It covered to southern Illinois. And we had a ragged line up through Montana, down through southern Illinois, through Ohio, into Pennsylvania and New York. But it was able to cover all of that region under up to a mile of ice in some spots. So an ice age is a time when alpine glaciers expand, vast ice sheets cover the northern latitudes. In the last billion years, we've had about 6 major ice ages. There have been a small minor ones, but basically 6 ice ages. They each lasted of up to 10 million years, and the most recent we call the Pleistocene Ice Age. The Pleistocene Ice Age started about 2.5 million years ago, and it ended about 10,000 years ago. So why do we care? If we are going to study something like climate change, we have to understand past climates. And one of the easiest things that we can do is talk about ice ages. Why? Because I've heard a lot of people say this, well, back in the 50s or the 60s, they were talking about the next ice age. Okay, well, we need to understand what an ice age is. We need to understand how that relates to climate. We need to understand the driving factors to know whether we are moving into an ice age, moving away from an ice age, whether they're part of the distant past, or whether what is happening now is anomalous. Every time, and maybe this might frustrate the heck out of people, every time I give a lecture, I always want to make sure people understand why we are doing things, because otherwise it's just, I'm talking at you and then people ignore it. Ice ages come in cycles. It's good, right? What causes those cycles? Well, here on the right-hand side, what I want to talk about is a graph and how graphs can be unhelpful. What you're looking at here on the far right-hand side, you are looking at geologic periods. We have a time scale, just like we could look at a human lifespan and we would go birth, toddler, adolescent, etc., teenager, right? The Earth is broken up into time slices, and those time slices are defined by fossils. And largely, the ends of them can be extinction events or demonstrable changes in fossils. So we've broken them up into a series of time slices. And all of those names there represent specific periods where the fossils were unique. We know, for example, in the middle there, Jurassic and Cretaceous. We understand, okay, that's dinosaurs, etc. Right? And we could spend an entire lecture talking about those. If you look at the left-hand side of that, what we have is time in millions of years before present. So 570 million years before present, 245, etc. Right? The reason why they're broken down into those time slices is also to show larger sections, what we would call the eras. We have, or the, yes, the eras. I always get eras, eons, etc. So they're broken up into chunks. Right? If you look at the top axis, it says estimated mean global temperature. This isn't angry, this is mean as an average. If we can come up with an estimated average global temperature, then what this is showing, it's very simply trying to show these are times that it was cooler than that, these are times that it was warmer than that. In that case, it's meant more as a schematic rather than a definitive, here's the temperature that we're looking at, here's the exact numbers. What you are looking at is an attempt to look backwards into the past history of the Earth, estimate temperature, and we're going to talk about how you do that, to look at warm sides, cool sides. It is not the most definite graph, right? We just have warmer and cooler, and we have some midline, and then we have years before present. Why would I give you such a vague graph? Well, in this case, it is to show that we have had warm periods in Earth history, we have had cool periods in Earth history, and then we've had fluctuations in between. If you count these on the screen, and I could point at the screen all day, starting from the top, which is the Pleistocene Ice Age, and going backwards, we have one in the Pleistocene, one around the Carboniferous, one around the Ordovician, Silurian, and then 3 in the Precambrian. And why does it bifurcate there and we have 2 lines? Well, the farther back in time we go, the less accurate it becomes. So there's a lot of open questions that we have around that time, which is 700 plus million years ago. What does that graph show us? It shows that if we are correct at measuring temperature, then what we have is a cyclical temperature scale. Sometimes it's colder, sometimes it's warmer. The Earth goes through phases, right? Now, there's another thing about this graph that is important, and this is really important. This has been like the old cereal boxes enlarged to show texture. If you notice, the scale, the left-hand scale there, is not a regular scale. 570 to 245 million, think about that. That is 330 million years. The next time slice, which is even smaller, is 180 million years. The next time slice, which is smaller, is only about 64 million years. And then that last time slice is 1.5 million years that we've just really enlarged. So this, if we stretch that to be accurate and flatten it out, the Pleistocene would be hard to see on there. It would be there, but it would be compressed at the very end. So we've sort of enlarged this to show the regional things. And that, whenever you're looking at a graph, you have to understand whether it's meant to be remarkably definitive or just general for general explanation. You need to know its purpose. I tell my students this. that if you ever have somebody and they point at a graph and they say, the data clearly shows, they're lying about something. Whether they're intentionally or unintentionally lying, they are, because if the data could clearly show that, shut up. It's going to show it. So I explained it to you, and I didn't say the data clearly shows. I tell my students that's also, I would call that the Jackie Channing of the world, because think about what you're doing. The data clearly shows, look at this hand, and the other hand is coming to punch you, right? Because it's misdirection. Whether that's intentional or unintentional, I've seen too many lectures where people go, the data clearly shows, and my immediate thought is, I'm now not going to listen to what you say, I'm going to read the graph. So what causes the cycles? And we're going to go through these, 2 in this lecture and 1 in the next one. Atmospheric conditions, so changing carbon dioxide, oxygen, et cetera, in the atmosphere, and changes in Earth motion, so our position around the sun, and volcanic eruptions. Those are our short-lived triggers that we're going to talk about in extent next time. Why? Because I do volcanoes for a living. All right? Here's a busy diagram. There's an incredible amount of information on this, and we're going to look at it in great detail. First of all, temperature and tidal. Temperature and carbon dioxide concentration in the atmosphere over the last 400,000 years, taken from the Vostok ice core. So what is this? This is a large cylinder of ice carved out of Antarctica from near the Vostok research station in Antarctica. Okay? We can see here 2 lines. The top line is carbon dioxide concentration. The bottom line is temperature change from present. So before we do anything else, let's talk about the word before present. If we have some concept of before present, when is present? Well, human speech, present is now. The problem with that is, if I say something occurred 150 years before present, next year it occurred 151 years before present, the next year 152. So if we are using this as a discussion point, we have to define what present is. And this is why it says years before present, where present equals 1950. Why? Because it takes 2 things. One, it was an agreed upon time to just say, here's present 1950. We didn't want to wait because many of the things we look at are radioactive isotopes, which changed perceptively when we started doing a lot of atmospheric nuclear testing. So after 1950, we stopped using that as a metric, right? Or we had to do other things to try and clean up the data because they started to get messy. So we argued that 1950 was a good time. Not as in it was a great time to be alive, but it was a good marker for history. We had a lot of the data to be able to then start tabulating all this information to be able to present it. 1950 was chosen. So if you look here, you're not going to see what is the modern changes from 1950 to 2020, which in this case would be, we would argue, would be some of the most important things for us to discuss for climate change. Right? But if you look, it goes back 400,000, 420,000 years. So let's look at that top line. Carbon dioxide concentration, parts per million volume. That's what ppmv stands for. So what does that mean? If we were to take a section of air, like all of the air molecules in a space like this, and we would count them up. If we could count up those number of air molecules, what we are saying is most of those air molecules would be nitrogen, some of them would be oxygen. Then we would get even smaller concentrations of carbon dioxide, argon, et cetera. We would have water in there in varying percentages, et cetera. How much of that air, if we just take a section of air, is carbon dioxide? How can we do that? Well, we have devices that can separate air in a very similar way to the way that we separate blood, because the molecules weigh different amounts, so we can separate them out by spinning everything up. That's one way we can do it. If you look at the left-hand axis there, what you are seeing is an axis that goes from 160 parts per million to 300 parts per million. And so what you are seeing is a spike. First spike, we see it as about 280 parts per million, then it drops to about 180, then up to 300, then down to the next lower point at 180, and it zigzags around like somebody's bad EKG. But what we can see is we get spikes, right? At about 420,000 a spike, at about 340,000 a spike, at about 240,000 or 30,000 a spike, at about 120,000 a spike, and then recently, right? Because if we're dealing with, yes, even though 1950 is that zero line there, anything that's really close to that is on the order of thousands of years, right? So what do we have? If you do the math on that, you break it down, and check me, because I'm not going to say the data clearly shows, roughly every 100,000 years or so, we get a spike in carbon dioxide. You see that? Roughly every 100,000 years or so. It's not perfect. If you notice there, we don't just get one giant V and then a point, and then another V and then a point, and then we don't get nice sawtooth consummate Vs. We don't get that. Let's look at the bottom. Temperature change from present in degrees Celsius. So notice what we have. We go from -10 degrees Celsius to 4 degrees Celsius. Why Celsius? Well, the international community, aside from the United States, but all scientists use metric system, which includes Celsius. Okay? So Celsius, roughly, if you look at Celsius, about 1.5 to 2 degrees Fahrenheit for every 1 degree Celsius. Not exact, but we're just going to work with that. So we're talking big temperature changes, because there's a major difference between 80 degrees outside and 60 degrees outside, or 60 and 40, or 40 and 20. There's a major difference there. Okay? Years or temperature change from present. So if we knew what the average temperature was in 1950, we go backwards in time and we can look at temperature. And before I want to address this. Your immediate question should be, how can we figure out temperature 400 and some thousand years ago? Makes no sense. Well, in a way that we can. If we can understand the relationship between temperature and carbon dioxide, now we have a relationship that we can use one to figure out the other. So one way that we can do this is this. If you look at the ice cubes made in your refrigerator, the ice cubes made in your refrigerator have air bubbles in them. And if you look at those air bubbles, sometimes the ice smells. Why? There's something wrong in the line, mildew has built up something, and you go, why? You can smell it because it's incorporated in the ice. When ice forms, when a snowflake forms, it is 80 to 90% air by volume, and that air is trapped inside the ice. When the snow falls and gets packed down, it gets denser and more compressed. Some of the air escapes, but some of it is just trapped there. In a glacier or an ice sheet, the ice traps that air. Some 20% of the ice is still air by volume. And that means that there are air pockets buried deep in the ice which have the scent of the refrigerator, if you will, preserved in them. So what can we do? We drill a long cylinder out of the ice, we remove the cylinder, we find the hole, the bubbles that are still trapping air from ages past in the ice, we stick a needle in and we can essentially harvest the gas. And then we separate it into its component molecules and we go, here's how much carbon dioxide there was by volume. Why? Because we now have one air pocket, and we do this many times. The Vostok ice core was hundreds of feet long because we wanted to go back as far as we could, and we took it back 420,000 years. There's actually a longer core that went back about 800,000 years, but we're only looking at the last 420,000. Why? Because we're trying to focus on one section of it, and then I'll show you later on temperature change over the last 800,000 years. We also have white blocks on here, pre-Illinoisan, early Illinoisan, late Illinoisan, Wisconsin, and before you say that's a bad misspelling of the state, these are looking at advances and retreats of ice during the last ice age. Wait a minute, I thought all of this was the last ice age. Yes, but think about a war. In a war, you are not actively fighting every second. For example, when we talk about the 100 Years' War, which lasted like 113 years, they were not fighting every single second of that. Sometimes there was active fighting, then there were periods of quiet. There were periods of active fighting, periods of quiet, active fighting, quiet, etc. In an ice age, what we're saying is from 2.5 million years to about 10,000 years ago, the atmosphere was sort of like, it was quivering, it was unstable, and so we got ice advances, and sometimes they would retreat, and then they would advance, and then they would retreat. They came down, they moved back, we built Hadrian's Wall, right? We have the idea of this advancing and retreating. And the white blocks there represent advances. The biggest push was the Wisconsin, came as far south as southern Illinois and obviously Wisconsin, and then pulled back. And then we haven't gotten an advance since then. And since it retreated to its farthest position in that last 2.5 million years, we say the war is over, the ice age is over. Okay? So logic. There seems to be a correlation between carbon dioxide and temperature. As carbon dioxide goes up, temperature goes up. As carbon dioxide goes down, temperature goes down. And when we get some of our lowest points of carbon dioxide, and therefore our lowest temperatures, we get advances of the ice. So there seems to be, and it is not a perfect correlation. Notice the temperature spikes become very narrow versus the carbon dioxide spikes, which are much more broad. A very astute observer here will notice one strange thing. The temperature change tends to precede by just a little bit the carbon dioxide spikes. So it looks like we get a temperature spike and then a carbon dioxide spike. Why? Well, in part, there are other changes. It's not just carbon dioxide. There are other changes, say what we do around the sun, which we'll get to in a little bit, that cause the temperature to increase. But as temperature increases, there are lots of processes that are temperature dependent, which have carbon dioxide associated with them. Decomposition, something dies, it breaks down. As it breaks down, carbon dioxide gas is released. When it's hotter, that process happens faster. So as temperature increases, more carbon dioxide is released. That tends to cause temperature to go up, more carbon dioxide is released, and so on and so on and so on. We go, well, wait a minute. Why wouldn't it just, if that's the case, why wouldn't it just run away and we'd be incinerated? Because one of the cool things is as temperature goes up, carbon dioxide increases, the rates of weathering, like all the damage done to tombstones and statues where they sort of break down and look moldy, that actually involves a chemical reaction which pulls carbon dioxide out of the air. So it's like a thermostat in your home. Carbon dioxide increases, certain processes get faster, which pull carbon dioxide out. Carbon dioxide decreases, temperature decreases. Does that make sense? So temperature goes up a little bit, that sets a ball rolling, like the avalanche has already started, it's too late for the pebbles to vote, right? It increases, then carbon dioxide increases, temperature increases, carbon dioxide increases up to a point until the processes that remove it from the atmosphere win out, and then it goes back. Thermostat in your home, it heats up, air conditioner kicks on, cools the house down to the temperature, shuts off, temperature heats back up, kicks the air conditioner on. That's the system that we think is going on. And there's a source down at the bottom, pages, book, etc., if you want to look at it. Now for another graph, right? Here, one of the things we have, let's look at the upper left-hand image. Near the poles, atmospheric water vapor is increasingly depleted in 18O, what we would call oxygen 18. Heavy 18O rich water condenses over the mid-latitudes. There's arrows and crazy things going. Okay. Oxygen has 8 protons, 8 neutrons. 8 plus 8 is 16. So when we talk about oxygen in the air, we're talking about oxygen 16. There is a form of oxygen which we call an isotope that has more neutrons. It has 2 extra neutrons. So now we have 8 and 10. We add that together, we get 18. Oxygen 18 occurs in remarkably small concentrations in our atmosphere. So there's oxygen 16, that's most all the oxygen which is going around, and then there's some oxygen 18. When we have the oxygen 16 and the oxygen 18, they have different weights. Why? Oxygen 18 has 2 more neutrons, so it weighs more. In colder periods, it is more difficult for the oxygen 18 to go into the gas phase, and then we put in ice. Why does that make sense? Well, think about it. We have water. Water is H2O. That oxygen, the O, could be oxygen 18 or oxygen 16. Most of it is oxygen 16. When we get warming, we get a lot of evaporation. We get a lot of oxygen going into the atmosphere. Some of it is oxygen 18, most of it is oxygen 16. In colder times, we're still getting evaporation and precipitation, but it is easier for the oxygen 16, the lighter isotope, to go into the atmosphere. So in colder periods, it's more difficult for oxygen 18 to go up. it is easier for oxygen 16 to go up. That gets snowed because water vapor can turn to ice. Ice is still H2O. There's oxygen 16 in the ice. So oxygen 16 tends to concentrate in ice in really cold periods. And where does the oxygen 18 stays? It increases in concentration in the oceans because it couldn't leave. Long-lived ice tends to be layered, showcasing warmer periods with colder periods. Some snow is going to be added to that ice. If the Earth is warmer, then more oxygen 18 gets kicked up into the atmosphere, so we'll get snow that has a higher concentration of oxygen 18. If it's colder, like during those pulses that we saw here on the screen, pre-Illinois and early Illinois, and etc., there it's colder. Any new ice that's added there would be expected to be more rich in oxygen 16 and depleted in oxygen 18. Why do we care? We talked about carbon dioxide. Well, if we're talking about long-term climate, we don't want one data point. We don't just want to talk about carbon dioxide. Oxygen should follow similar models, right? We want it to follow similar models. The cool thing about oxygen 18 is this. In living organisms, there is oxygen in your body, logically, which means some of it is going to be 18, some of it is going to be 16. As it moves through the system, you're going to inhale some of both. In colder times, organisms should uptake more oxygen 16 and less oxygen 18. And if it gets incorporated into your bones and your hard shells, right, for sea creatures, for example, we should be able to see that in the shells of sea creatures, in the bones of once living organisms, in fossils. So, by God, here's a busy diagram. This is one of those things about climate change. If somebody presents to you a graph, don't listen to them, right? You might not listen to me. And look at the graph, try and understand what it means. Because there is a tendency to try and wow people with science. I've obviously done my homework because I have this busy graph. So what does it mean? Doesn't matter. He's obviously done his homework. Listen to him. Okay, so we saw those time periods a long time ago. Here they are listed on the screen. The J, for example, is Jurassic. The K, for example, is Cretaceous. And then we've lumped all of the other ones that are closest to our most recent time scale as PG, Paleogene, and N, Neogene. That's on the upper left-hand corner there. So our most recent thing is the Neogene and the Paleogene. We go, wait a minute. I'm lost here. Sure, Phanerozoic climate change. What's the Phanerozoic? That encompasses all of this. Our most recent, if you notice, the far left is 0, recent. The far right is ancient, okay? 542 million years ago. Why did we flip the graph? Different people made different graphs. Are they trying to hide something? No. It's just the ease of presenting the information. It isn't that they're trying to screw with us by moving the graph around. Does that make sense? This gets into an important concept. One of the things, and this is the reason why I did this, one of the things that makes climate change so difficult to discuss, or any big topic to discuss, if you have people just throwing stuff at your face, then you get confused, okay? Left-hand side of the graph, changes in oxygen 18. That's what that symbol is, 18O, parts per thousand. So if we are comparing oxygen 18 to oxygen 16, we are looking at the changes in oxygen 18 in parts per thousand, okay? Remember what we said, in times of cold weather, we get a bigger change in oxygen 18. There are too many isotopes. We get a bigger change in oxygen 18. What does that mean? We tend to get depletion of oxygen 18 in glaciers. So we get a change on this one that we've lost oxygen 18. And that's what a positive numbers in this case, we've had a change away from our 0, okay? In hotter times, more oxygen 18 is kicked up, so hotter times here is negative. Why? We have a loss from the oceans, a gain elsewhere. Okay? So if we look here, remember we talked about 6 glacial periods when we started talking about ice ages. Here are 4 represented. The other 2, remember, were in the Precambrian, which is not shown on this graph at all. It's off to the right somewhere off the graph. If you look at the bottom axis, millions of years. Here's another thing about climate change information. Notice this is in millions of years, whereas the last one was in hundreds of thousands. Why? Different data trying to show something different. But if you are not paying attention, then you go, oh, we're looking at the same thing. We are not looking at the same thing. Okay? What we were looking at last time covered this section right here on the far left side of the graph. It's important. Why? Why would I do this to you? Because I want to try and show something. Okay, so what did we see? Carbon dioxide decreased and increased and decreased and increased and decreased and increased. Temperature seemed to follow that, and there was some reciprocity between them. Here, let's look at larger scale. Why? Eventually, we run out of ice. The farthest back we've been able to go with the ice is about 1 million years, which would be on this period right over in here. I only showed you 400,000 years of it. If we want to understand truly epic things, to say, well, maybe just the recent history of Earth, recent in 400 or 800,000 years, is too crazy, then what about the longer term stuff? Let's look back at the longer term stuff. Then when we actually look at the graph, we have hot and we have cold. Okay, that's not exactly very descriptive. Along the bottom, we have glacial periods, right? Why different colors? Some are more severe than others. Some are much more benign. Okay, so we have periods of ice. We have periods without it, periods of ice, periods without it. Okay. We can only go so far back with ice cores. We can go farther with oxygen measurements in the shells of dead sea creatures and the bones of land creatures. Okay. So now, what does all this stuff mean? Well, we have three things going on here. We have blue, black, and gray. We have blue short-term average, black long-term average, and these gray bands. Here's the reason. In order to come up with a graph that's like this, one person could make the graph, but one person cannot collect all that data. Too many sea creatures, too many eras, too many periods of Earth history, too many areas of Earth. This is the labor of love from somebody that received data, published data, and unpublished data, data that had yet to make it to publication, pulled all this data together to try and come up with one consistent picture. This is a bunch of labs all doing a bunch of individual research to try and understand the climate of their period in history, whether it's the Jurassic or the Triassic or the Cretaceous or whatever. And they're trying to put all that information together to make one consistent picture. What do the averages mean? Well, the blue average is averaging the data over a 3 million year time scale. Why 3 million? 3 million is huge, but when we're dealing with 542, is it really that huge? So what we took is we tried to average the data over 3 million years, and what we see is we have these saws. We have higher periods, lower periods, higher periods, lower periods. So we get oscillations in the amount of oxygen-18. The long-term average is averaged over 15 million years. Take the same data, but averaged over 15 million years, and we get a much smoother curve. Makes sense. If we take data and the bigger the averages, the bigger the grouping of data that we attempt to average, the more smooth it gets. This makes logical sense in another way. If we are trying to patent a drug to release to the American public, we want to test the most people possible. If we only test a few people, they might be unique in their reaction to it. But if we test tens of thousands of people with that drug, then we have a better understanding about how it works for a population, and the effects, the extremes get sort of muted out. And that's what we're trying to see here, long-term and short-term. The gray represents the errors associated with our measurements. Because anytime you take any measurement, the device is only so accurate. The individual samples that you get, maybe there's something wrong with them. Maybe you didn't get the best sample. Maybe you couldn't find better samples. So our devices that we measure with have errors associated with them. And that gray area is 95% confidence. So we are 95% confident that our average falls in that gray band. In some areas, we are less confident. In other areas, we're really confident. Notice the closer we get to more recent times, the more accurate we get in general. So what do we notice? Oxygen-18 goes through highs and lows, right? Whenever we get a high, we tend to not have glacial areas, glacial periods. Whenever we get a low, we tend to have glacial periods. So who cares? The more data we have, the more it shows that climate change, at least over the last 542 million years, and then if we zoom in on that last little bit, it comes in cycles, right? Without people, or even with people, without any major industrial machine going, it comes in cycles. So it is cycling even without people. We'll come back to that later. Let's do 3 things to talk about Earth changes. And these are egregiously schematic. They're not meant to be fundamentally accurate here. But if you look at the upper left image, or yeah, the upper left image, you see 2 things, a dashed line and a circle and a dashed line and an ellipse. The sun is in the center, and then we have 2 Earths, tilted because the Earth is tilted on its axis. Every 100,000 years, we change from a more circular orbit to a more elliptical orbit. Now, the change is not great, right? It's only about 4% of the total distance. So we go from, say, this length to that length, and this length to that length. So we only change by about 4%. But it is enough if 1/2 billionth of the sun's energy is enough to cause major climate changes on Earth, or to affect the daily life of Earth, then getting closer to the sun or farther away from the sun is dramatic, or could be dramatic. So what we tend to find is that when we get a more circular orbit, the seasons are much more muted and mellow. Why? Because every place that we have is, every time as we move around the sun, we're about the same distance from it. The more elliptical we get, the farther we are from the sun in orbit, we tend to get more extremes, because then we go from a closer to a farther, because it's elliptical. So we have closer, farther. We call that eccentricity. You might have heard that term, orbital eccentricity. Right? That varies about 100,000 years. About every 40,000 years, 41,000 years, we get a change in the Earth's tilt. It's only about 2.4 degrees. Right now we are sitting at 23.5 degrees from vertical. So vertical, 23.5 degrees tilted. The more vertical we are, the more muted the seasons are, because if we were vertical, then every place would get 12 hours of sunlight every day, and the distance from the sun, then all we'd have would be minor variations, and then the areas that would be cold would stay cold, the areas that were warm would stay warm, etc. But because we are tilted, if that tilt changes, the more vertical we are, the more we are to a sort of uniform planet, the more tilted we are, the more extreme, because then we get more direct heating of the Arctic and not of the Antarctic, and vice versa. We call that obliquity, literally the tilt, or the obliqueness of the tilt of the Earth. Every 26,000 years, we actually spin on our axis like a top. Now, when you say, wait a minute, don't we always spin on our axis? The axis itself is moving, because if I think about a top spinning, when I start spinning the top, it's vertical. When I spin it and it starts to wobble, it spins on its axis, and then its axis itself moves, and so it moves around the table. So if you notice here, it shows June. Well, in June, the northern hemisphere is tilted toward the sun. That's how we get summer. 26,000 years from now, June will actually be, in our winter, will be facing away from the sun, and the southern hemisphere will get its summer. Really? The seasons can flop like that? Absolutely, because we are a top, which we are constantly spinning on our axis, but the axis itself is tilting, it's wobbling back and forth, and it's pointing in different directions. We call that orbital precession, and that is 26,000 years. So why do we care? Now we have something at a 100,000 year time scale, and something at a 41,000 year time scale, something at a 26,000 year time scale that can all influence our climate. Sometimes they reinforce each other, sometimes they cancel each other out somewhat. Why? If we were more eccentric in our orbit, more elliptical and more tilted, then we would get more extreme seasons. If we were more vertical and more circular in our orbit, we would get less extreme seasons. But sometimes we are more tilted and circular, so they sort of mute each other out a little bit. And that can have, we call those the Milankovitch cycles, after the scientists that sort of identified and started the work on those. forget what his first name was, but Milankovitch. And why do we talk about those? Because a Milankovitch cycle, these cycles can have a profound influence on Earth's climate. So what have we done? We've done atmospheric changes, carbon dioxide, oxygen 18, and then we've done planetary changes. Why? If we are going to talk about climate change, we have to look at all of the things that could change climate. So we have to look at stuff the Earth does without us, atmospheric changes, right? Stuff the Earth does without us, orbital changes, and then stuff the Earth does without us in the next lecture, volcanic changes, short-lived. Because then we can again go to the third lecture, we talk about modern changes. What are we seeing now? And is this unprecedented in Earth's past? So I want to thank you all for joining me here. You're going to be watching this video after I sign off. Obviously, I'm going to post it after I sign off. If you like it, we're going to do subscribe, give the thumbs up, leave a comment. If you have questions, put questions on the YouTube page. I'm going to post this, and I want people to ask me questions. And here's one more thing. When we look at a discussion like this, I want people to understand one thing. It is a complex topic, but if it is so obvious, the changes, the threats, the response that is needed, if it is so obvious, then it shouldn't just be something that climatologists and only climatologists can make statements about. If we are scientifically trained people, if we have a love for science, if we are willing to investigate, then we can do it for ourselves. Thank you.